Welcome to our fourth module in the Introduction to Doka for DPUs DLI course, called Doka Development Environments. In our previous module, we went through the steps to set up a Bluefield-2 DPU to get the host and the Bluefield set up correctly with the Doka SDK software to be able to both write and execute or test Doka applications. In this module, we'll cover some more of the developer experience and share some examples of building code in a few of the different environments, depending on your CPU architecture. Let's get started.
In this module, we'll open with describing a little bit about the Doka developer experience in general. After that, we'll look at two ways to develop for ARM architectures by looking at an example of building one of our included reference applications. Then, we'll also see an example of compiling and building a Doka application on the x86 host. Doka is not a closed API ecosystem. Developing for Bluefield-2 DPUs does not mean you lock into a single development environment. Bluefield-2 DPUs directly support many open APIs like DPDK, Linux TC, and OVS offload, gRPC communication channels, or any standard Linux monitoring service. The goal of Doka API libraries is to make many aspects of the development process easier, faster, and more flexible. The libraries Doka provides enables two functions, either building on top of existing APIs like DPDK to simplify them, extend them, and accelerate their development when moving faster than the community can. The other is to provide access to some of the custom accelerators and engines that we have on the DPU that do not have standard API implementations, like our storage hashing and host introspection capabilities. Again, Doka is an abstraction layer intended to make development for DPUs easier. Doka provides two different development models. One where applications are compiled for and run directly on the ARM CPU. This may be for isolation or for a specific offload function, for example, a security agent that needs to be isolated from the x86 host. A second where Doka libraries and runtimes are embedded in the x86 application and are used to communicate with the acceleration and offload engines on the DPU. This may be something like using Doka DPDK libraries to accelerate an NVF function. Bluefield DPUs utilize an ARM CPU, so that all applications that run directly on the DPU must be compiled for ARM architecture. Of course, if you have an ARM server sitting in your office running Linux, you can download the Doka libraries and start building right away. But to enable Doka developers, we've built the Doka development container, which packages a number of build tools, the Doka libraries, and a QEMU emulation layer to allow you to compile Doka applications for ARM CPUs on x86 hosts. This is to help make Doka application development fast, easy, and error-free. As we've discussed in previous modules, the Doka for DPU imaging and first-time setup process includes all of the Doka SDK libraries, drivers, and source files necessary for development. As an example, we saw the Doka URL filter sample application in the previous module, but let's compile and run that application from source using the DPU as a development and build environment. Starting logged onto the DPU, first, let's change to the root user because we'll need to access some of the sysfs to make a few configuration changes to support the Doka DPDK applications. All of these instructions for building the sample applications can also be found in the DevZone documentation under the URL filter sample application. Now, we'll change to the sample application source path at /opt mellanox doka examples URL filter source. Here, let's set the package config path environment variable to point to the DPDK packages path to support the underlying DPDK dependencies. but this step can be performed at any time from our working shell prior to build. From here, where the meson.build file is, we can simply issue meson build to build the application. This will create a build directory that we'll need to change to. Then by running ninja, we can compile and link the application to create our executable Docker application. To run this and most other sample applications, it requires two interfaces: an ingress and egress interface for the application to pass packets between. For demonstration, we can use the two scalable functions provided by default. We'll need the auxiliary device index to provide to the Docker application, and we can find that by checking the command mellanox-sf-a show, where we should see two entries and be able to locate and confirm the auxiliary device index for launching the Docker application. Lastly, we'll need to enable huge pages for DPDK packet processing and ensure that the regular expression engine is enabled, since the URL filter is a Docker DPI library application that leverages the hardware regular expression engine. These commands are in the SDK documentation for reference. Now, with the runtime environment configured correctly, we can go ahead and execute the application that we built. We'll need to provide a few of the PCIe devices on the command line to reference our two network devices as well as the regular expression accelerator with the -A flag. The -C3 flag instructs the application which cores to run on. And with that, our sample app is successfully running build from source on our DPU, which also doubles as a development and build environment. Now, let's take a look at the other option for developing applications to run on the DPU ARM cores, using the build environment container. For more rapid development for ARM architectures, NVIDIA provides a Docker container to run on x86 hosts that provides an ARM emulated environment to allow developers to build and compile applications for ARM without the need for ARM hardware. It's important to note that this container simulates the DPU software environment, but it is missing all of the underlying hardware and drivers necessary to run Docker applications. Thus, this container is for build and development only and cannot be used for testing. The high-level steps are fairly simple. Download the container, set up the ARM emulation environment. If you've already got an ARM-based machine, this isn't necessary. And then load the Docker image and go. Let's walk through the process of setting this up. Here, we'll step through the process of setting up this development container on an x86 host. Again, all of the instructions for setting up this container and this environment are also in the DevZone documentation in the installation guide in the section Setting Up Build Environment Container for Developers. There are slightly different steps to set up the container depending on your OS. In this example, we're running Ubuntu. To get started, we'll want to make sure we download the container archive file from the installation page on Docker DevZone and staged on the host. Now, back on the host with our tarball present and ready, we can begin the setup steps. First, ensure that Docker is installed. Running Docker version is a quick way to check. If Docker isn't installed, visit the official Docker engine instructions at docs.docker.com for specific instructions to set up Docker on your operating system. Next, we need to install QEMU and a few other dependencies to support ARM emulation inside of QEMU on our Ubuntu host. Now, with those changes, let's ensure Docker is started and running. Then, we can issue the docker load command to import and install the Docker image on our host. Now, with the development container loaded, We can run the container, but before we do, we'll want to think about how we map our Doka code project path on our local machine into the container. This way, you can seamlessly change files on the host side, and then build and compile in the ARM emulated container from the same project directory. Let's map the Doka examples into the container. The path is /opt/mellanox/doka/examples, and that path will be mapped into the container at the /app directory. These volume mapping settings are controlled by the -v option in the docker run command, and this looks good, so let's go ahead and run the container. The container will start running and drop us into a bash shell, and before we can confirm, let's check with uname-a that we're in the ARM environment. From here, if we change to our /app directory and list what is here, we'll find that we're in the Doka sample app directory back on the x86 host. If we want to build the DNS filter application, let's change into that directory, then source. Then, just as if we were on the DPU itself, we have to set the package config path environment variable for Meson to find the DPDK dependencies. With that set up, now we can issue a Meson build, and after that succeeds, change into the build directory and run Ninja to create our application. Remember that we cannot execute this application in this environment, so our built application would have to be moved to a DPU for testing. But if we inspect the application with the file command, we can see that it's been built for ARM, and we've successfully cross-compiled an ARM application on our x86 host inside of the Doka build container. Lastly, it's important not to forget that Doka applications can be written for and run against either environment, either on the host itself or on the DPU depending on your application and use case. For developing for x86, in the same way that the Doka SDK is ready to use in our other examples from Bluefield Bringup, the tools, libraries, and drivers are also all in place and all set up with the Doka SDK package installs that we walked through in the previous module for DPU Bringup. Let's look quick at an example of building a sample application for x86. Again, starting with the root shell on our x86 host, if we browse again to the Doka example directory at /opt/mellanox/doka/examples, let's compile and run the Doka NetFlow library example application. So we'll continue into the source directory. This sample application is built on DPDK and creates an easy-to-use framework to send NetFlow v9 records to a NetFlow collector over a UDP socket out onto the network. This example creates a sample NetFlow record and sends 40 copies of the record in batch. After changing to the source folder, ensure that you set the package config path environment variable to the DPDK packages path, ensuring that we use the correct architecture here on the x86 host. After setting up that environment variable, just like the other examples, we can go ahead and call Meson build to set up our build definition for the application. After completion, cd to the build directory and run Ninja to build and compile the application. The result is our linked and ready to run sample application, and we'll go ahead and execute it. As the output reports, it ran successfully and completed sending 40 sample NetFlow records, and we can confirm that we have a successful build and runtime environment for Doka development on our x86 host. In this module, we discussed the different Doka development environments available to build, compile, and run Doka applications. It's important to remember that the Doka SDK and runtime are supported for both x86 architectures as well as ARM, and thus Doka applications can be run on either the x86 host or the DPU itself. We walked through some examples of each of the main development environments by building and compiling some of the Doka reference applications in these environments. Thanks for joining us, and we'll see you in the next module.